Okay, welcome to this next lecture on sound and structural vibration. We ended up last time at this stage of the power integral. So we are going to move ahead. Okay, so we will do now the B integral. Okay, and looking at the B integral, we have just the B integral. Zero to B integral. Okay, so let's see that. So we have integral 0 to B e to the power I n pi y by B minus e to the power minus I n pi y by B by twice I e to the power I n pi y1 by B minus e to the power of minus I n pi y1 by B by twice I e to the power of I alpha k a y minus y1 sin theta dy dy1. Okay, so I get a minus 1/4 in front, okay, and 0 to B e to the power I n pi y by B e to the power of I alpha k a y minus y1 sin theta minus e to the power of minus I n pi y by B e to the power of I alpha k a y minus y1 sin theta e to the power of I n pi y1 by B n pi y1 by B dy dy1. Okay, so this will result in 4 terms. Okay, so this with this and this gives 2 terms, this with again this and this gives 2 terms, so you get 4 terms. So let's just look at one term. Okay, let's look at one term, which is this, the first term with the first term here. So there will be many similarities, and so I'll just go through one term. Okay, so the one term is T1, which is given by integral 0 to B the y dimension of the plate, okay, e to the power of I n pi y by B e to the power of I alpha k a y minus y1 sin theta e to the power of I n pi y1 by b dy dy1. Okay, it's a pretty simple integral. Okay, y and y1 they separate out because of the exponents, so they can be done separately. So I will not show it entirely, or you can do it in Maple if you are not confident. So you get minus 1 to the power n e to the power I alpha k a b sine theta minus 1 into minus 1 to the power n e to the power of minus I alpha k a b sine theta minus 1 in the numerator, and in the denominator you get minus 1 into n pi by b whole squared. Okay, minus alpha squared k a squared sine squared theta. Okay, that's T1 for you, one of the terms. Okay, then let me just say that T2, T3 and T4 have the same numerators. They have the same numerators, which simplifies to what? Each of them have the same numerator, minus 1 to the power n e to the power I alpha k a b sine theta minus 1 to the power n e to the power of minus I alpha k a b sine theta. This is the numerator. Okay, and what are the denominators? The denominators, one has a doubling, say, so you get minus twice n pi by b whole squared minus alpha squared k a squared sine squared theta minus 1 by n pi by b minus alpha k a sine theta whole squared minus 1 by n pi by b plus alpha k a sine theta whole squared. Okay, so this is like a plus b squared, a minus b squared, a plus b squared. So it's a square minus b square whole square. Okay, so if you now combine this, what do you get? You will get a minus 4 n pi by b whole squared, okay, divided by n pi by b whole squared minus alpha squared k a squared sine square theta whole squared. That's from the denominator. Okay, so to this denominator, this numerator must be put in front. So if we do that, if we put the numerator also in front, Okay, so what do we get? We get into twice minus 1 to the power n e to the power I alpha k a b sine theta minus 1 to the power n e to the power minus I alpha k a b sine theta. Okay, so this is now all 4 terms. Okay, and you have minus 1/4 in front, if you remember, minus 1/4 in front. So this minus will go with this minus, this 4 will go with that 4. Okay, so this is what we are left with. So let's see what we are left with. We have n pi by b whole square, which I say is my kpy squared. Okay, and the rest is of course e to the power I b alpha k a sine theta by 2 plus or minus e to the power minus I b alpha k a sine theta by 2 whole squared. Okay, in front I have a plus or a minus, okay, divided by k square py minus alpha square ka squared sine squared theta whole squared. Now what are these plus and minus? You remember we have minus 1 to the power n everywhere. Okay, so if n is odd, you take the plus everywhere. If n is even, you take the minus everywhere. Okay, so that's how this thing goes. Then now how does this whole thing look like now? It looks like this. The power looks like e by twice pi integral 0 to 1 4 m square pi square by a square, then either cos square or sine square of a beta ka by 2, cos for odd value of m, sine for even value of m, divided by m square pi square by a square minus beta square ka square whole squared. Okay, then we had a pi integral left minus pi to pi, and the b integrals were done. Okay, so the b integrals gave us 4 k py squared again cos squared or sine squared, okay, then b alpha k a sine theta by 2, cos for odd values of n, sine for even values of n, divided by k square py minus alpha square ka square sine square theta whole squared. Okay, and alpha d alpha by square root of 1 minus alpha squared. Okay, now finally this has a certain repeatedness over 0 to pi by 2. This integral is going from minus pi to pi, so over full twice pi range. However, it has a certain evenness about 0 to pi by 2, so that it repeats, and so we will write it as 4 times that. Okay, so when we do that we get an extra 4, so we write it as e over twice pi integral 0 to 1 4 m square pi square by a squared cos squared sine squared of this divided by kpx squared minus beta squared ka squared whole squared. This is kpx squared. Okay, then integral 0 to pi by 2 and hence another 4 into 4 k square py. Okay, then cos square sine square b alpha ka sine theta by 2 divided by k square py minus alpha square ka square sine square theta whole squared. Alpha d alpha by square root of 1 minus alpha square. Okay, so next if we bring everything, all constants, we start bringing all constants to the front, so my p of omega is equal to e into twice m square pi by a squared into 16, I brought it in front. Okay, k square py integral 0 to 1 the cos square term or the sine square term divided by kpx square minus beta square ka square whole squared integral 0 to pi by 2. Okay, again cos square or sine square of what, this beta alpha ka sine theta by 2 divided by k square py minus alpha square ka square sine square theta whole squared. Okay, alpha d alpha by square root of 1 minus alpha squared. Okay, e if you recall, okay, was E was what? E was given by rho 0 rho a c k a square v 0 square by 4 pi. That was my E. Okay. So if I bring that in here, what do I have into the power? I have E comes in down here, rho a c k a square by 4 pi v 0 squared. Okay. Now this twice and m pi by a whole squared. That means I brought in one extra pi. I lost a pi, so I brought in a pi. So I divide by a pi. 16 by pi. Then k square py. Okay. So this is then k square px. Okay. And the remaining terms. The remaining integral here and alpha d alpha by. Now what did I say earlier? I said my v tilde pq squared, space and time averaged mean square velocity, into my r rad is power, and that is equal to all of this. So for now it is rho a c k a square v 0 square, okay, 32, so 8 by pi square into kpx square k square py into this two integrals. Now vpq square is 1 over 8, I have shown you that. So it is equal to v0 square by 8, space and time averaged is equal to. So if we cancel the v0 square and bring the 8 up there, then my r rad becomes equal to rho a c k a square into 64 by pi squared kpx squared kpy squared into, let me just write once here, 0 to 1 c squared s squared a beta k a by 2 by kpx squared minus beta squared ka squared whole squared into 0 to pi by 2, again cos squared sin squared b alpha k a sin theta by 2 okay. So I keep forgetting d theta, sorry. Did I forget d theta? Yeah, so d theta must be there. The other differential, sorry. Okay, so d theta divided by k square py minus alpha square ka square sin square theta whole square. Okay, into of course alpha d alpha by square root of 1 minus alpha square d theta. Okay. Now beta square is equal to 1 minus alpha square, okay, or beta is equal to square root of 1 minus alpha square, or d beta is equal to 1 over 2 square root of 1 minus alpha square into minus twice alpha d alpha. Okay. So now when alpha is 0, beta is 1. When alpha is 1, beta is 0. Okay. So the sign change on beta, on the limit change on beta, okay, beta now goes from 1 to 0. Okay. So if I use the sign change and 1 to 0, I will still get here, so let me write 64. So R rad now is 64 by pi square rho a c k a squared integral 0 to 1, okay, k square p x by k a fourth into k square p y by k a fourth c square s square half beta k a into a by beta square minus k p x by k a whole squared integral 0 to pi by 2 c squared s squared half alpha k a b sine theta by alpha sine square theta, okay, alpha square sine square theta minus k p y by k a whole squared d beta d theta. Okay. So this is a form that the paper by Maidanik has. So this is the basic or the central radiation resistance integral. So from here he starts to make approximations for various modes and various frequency ranges. Okay. And largely these approximations are intuitive. Okay. So at least in the paper only a few details are there. I am closing the lecture here. Thanks.